So, before we actually go and study phase diagrams directly, first of all we need to make ourselves familiarize with language of phase diagrams. So, we should understand different terminology that one would use when dealing with phase diagrams. That is what we will do in the following. So, the basic definitions, first of all we need to understand what do we mean by a system, right. So, system is nothing but a series of possible alloys consisting of the same components, which means if you have an alloy made of A and B, there are different kinds of possibilities possible, right. So, what is the weight fraction of A and what is the weight fraction of B? You can have 100 A, 0 B is pure A, that means 100% A, nothing, there is no B, and you have 0 A, 100 B is pure B, and in between you can have all combinations, right. For instance, 90 A, 10 B, 10 A, 90 B, and you can have, in principle you can have infinite such combinations. So, series of all such possible alloys consisting of same components A and B, but having different compositions. Such system, such a possible alloys are called, can be considered as one system. For instance, if you take iron and carbon, all combinations of different weight fractions of carbon in iron is called iron carbon system, right. And then what is in the system, what do you mean by component? The component is basically the pure metals. So, for instance, if you are making a alloy system out of A and B, A is pure A and pure metal B, and this is called one component, B is called another component, right. So, the component is nothing but pure metals or compounds, of which it need not be only pure metal, sometimes it can be a compound also. So, one of them can be a compound, another can be a pure metal, and so on. So, if you are making an alloy out of these things, so these pure metal or compounds are called components. So, for instance, your solvent and solute, for instance, if you take a two component system. So, if you take A and B, if there are only two components in an alloy, there are such a system is called binary system, and in this class we will only be dealing with binary system. Okay. And what do we mean by phase? A phase is nothing but the way that the phase should be defined is the homogeneous portion of a system that has uniform physical and chemical characteristics. A phase is nothing but a homogeneous portion of a system that has uniform physical and chemical characteristics, that is what we call a phase. So, suppose if you take a solid solution of A and B, in the liquid state it has certain properties, uniform physical and chemical characteristics in the liquid state, and hence it is called liquid phase. If it is coming in the solid phase and if it has uniform physical and chemical properties, then that is called another phase, right. And you can actually have multiple phases in a liquid state or a solid state, and we will see, that means when we say multiple phases, each phase has a specific kind of physical and chemical properties. And what do we mean by a homogeneous system? Homogeneous system is nothing but a system which has only a single phase, and mixture or heterogeneous system is the one which has multiple phases. And we know already the definition of solvent and solute, we have already looked at it in the previous classes. So, solvent is the component in larger portion or the host, and solute is the component that gets dissolved in the solvent, or some component can be, solute can be thought of as guest, which is actually coming and sitting amongst the solvent cloud or host cloud. Alright. So, next we will try to understand the important concept called solubility limit. As we have discussed, there is a limit to which you can add a material A to material B and vice versa, and that is what we call a solubility limit. So, at a specific temperature, the maximum concentration of solute atoms. What is the maximum concentration of solute atoms that can be dissolved in the solvent to form a solid solution, and that is what we call solubility limit. So, the maximum concentration of solute atoms that can be dissolved in the solvent to form a solid solution is called solid solubility limit. For instance, we can take the example of sugar water system. Here in this graph, the red curve here, this curve here shows the solubility limit of sugar water system. Okay. So, the left to lead, so here we are seeing the temperature on the y axis and the x axis you have composition. Okay. So, left to this red curve, the sugar water system is in liquid solution, and right to that red curve you will have some liquid solution and some solid sugar. Okay. So, this is liquid solution and here you will have still some solid sugar, right. So, left to that it is a single phase region and right to that you have two phase region, one liquid and one solid phase, and the components are water and sugar. So, left to that only liquid solution exists, right to that both liquid solution and solid sugar coexist. And as you can see, for instance, if you take let us say this composition, at this composition you can clearly see that at 0 degree Celsius we are in two phase region. That means there is more there is liquid solution and some sugar. So, why there is solid sugar? Because the solubility limit is this. That means what? It can only hold this much, the weight percentage of sugar, or what it is shown here is, here so sugar is 0, 100 sugar. So, at this point, at this temperature, the solubility of sugar in water, the maximum solubility of sugar in water is about 61, but we are talking about an alloy composition having 62% sugar, let us say somewhere here. Then we see that we are oversaturated. So, the additional thing, because it cannot dissolve more than 60% at 0 degree Celsius, the remaining thing will be there as solid sugar. But now at the same composition, if you increase the temperature, by the time you increase the temperature around say let us say this is 10 and let us say 13 degrees Celsius, then you have reached the saturation. That means, at about 13 degrees Celsius your sugar water syrup, the water can hold 62%, let us say this is 62%, 62% sugar syrup. And if you further increase the temperature, whatever solid sugar that was there before is actually transformed to liquid solution. So, it has got dissolved in the liquid because the solubility now is higher than what you have as your alloy composition. This is typically what you must have observed when your mom tries to make some sweets made of sugar. So, they add sugar and water and put it on in a pan and put it on a stove. When they keep on increasing the when they keep on heating, after some time the sugar gets dissolved in water, right. So, the reason why it gets dissolved in water is because you are increasing the temperature of the solution. As you are increasing the temperature of the solution, the solubility of sugar in water is increasing, as we have seen in this graph, the red line, right. So, the point is that at a given composition, the solubility need not be constant, it will be a function of temperature. As you increase the temperature, the solubility in this case is increasing, solubility of sugar in water is increasing. So, the solubility limit increases with increase in temperature for this sugar water syrup. And what do we mean by equilibrium? So, when we say a system is in equilibrium, if its free energy is at a minimum, the free energy of the system should be at a minimum, and macroscopically when some system is at equilibrium, the characteristics of the system do not change with time, that is the key. If you see a component at equilibrium, as a function of time, if you are seeing that component today and come back after 100 years, it will still remain the same if it is in equilibrium state. Okay. So, the characteristics of the system should not change with respect to time, and such a configuration is called equilibrium configuration, or such a system is said to be in equilibrium. And what do we mean by phase equilibrium? Phase equilibrium is nothing but the constancy of phase characteristics. As we have seen, there are in the liquid sugar water solution, you have in the liquid state, you have liquid solution, in the solid state you have two phases, liquid phase as well as solid phase. The constancy of phase characteristics, that means the characteristics of the phases should remain constant with time. Okay? But at a given temperature, but if you are increasing the temperature, so for instance, if you increase the temperature of sugar syrup, say at 30 degrees Celsius in contact with solid sugar, if you heat it to 100 degrees Celsius, suddenly what happens? The solubility limit increases and then the phases do not remain the same, the phases change with respect to time, and then it is then we say that the phases are not in equilibrium, because they are changing with respect to time when we are increasing the temperature suddenly. Okay? And then very important state called metastable state. What do we mean by metastable state? It is actually a non-equilibrium state, but with very long time for changes to occur. That means it takes sufficiently long time for changes to occur. For instance, if you take an iron rod and leave it in open atmosphere, right? Maybe in 1 or 2 days, if you come back and see, you may not observe a significant change. But if you come back and see maybe say a month after or a year after, then you will see that the iron is actually getting rusted. That means there is some change is happening to the phases that are present in the system, because of which the iron is rusting, and hence, but this change is happening over a long period of time. It is not happening over a short period of time, and hence such a state is called metastable state. So, it is a non-equilibrium state, but the changes are happening over a long period of time. And please note that for any system that we are, for any alloy system that we will be discussing, the perfect equilibrium does not exist. So, all the equilibriums that we are mentioning are usually metastable states, because over a long period of time, that long period may be few hundred years sometimes, right, but nevertheless even after few hundred years there may be some change in the phases, right, and such a state is what we call metastable state. And we know that the properties of a material or an alloy, in this case as we have discussed so far, to a large extent depend on the type, number, amount and form of different phases. What type of phase it is, how many phases are there, what is the weight fraction of each and every phase, and what is the microstructure of these phases. Okay? All these determine the properties of the material. Okay? And it is important to know the condition for existence of these phases. So, suppose let us say a particular phase is going to give you a desirable property, and as an engineer we should know what are the conditions under which such phases become a reality, that means they become viable or they exist, and what are the conditions for change of phases. So, you got some phase, and what are the conditions under which a particular phase changes to some other phase. So, this information is something that one needs to know in order to be able to use the alloys with the utmost efficiency, as we know. So, the phase changes in many alloy systems is best described by phase diagrams. The phase diagrams are also called equilibrium diagrams or constitutional diagrams, they are synonyms. The phase changes that we are discussing, we have posed the question in the previous slide, how the changes occur, and the answer to that is usually given by understanding the phase diagrams, or phase diagrams give answers to the question on how the changes occur from one phase to another phase and under what conditions. And the physical properties required for complete description of equilibrium phases are pressure, temperature and composition, right. So, these the phases that we are discussing in an alloy system depends on these three independent variables: pressure, temperature and composition. So, now let us look at for the sake of understanding a unary phase diagram or one component phase diagram. So, that means there is only one component, that is what is known as unary phase diagram. Here we are looking at the phase diagram of water. So, here we are having, because it is a unary phase diagram, the composition does not come into picture. When the composition comes into picture, when there is more than one component, right, because there is only one component, it will be there 100%. So, the composition does not come in picture, and hence the other two variables are pressure and temperature. So, here on the y axis we have pressure, on the x axis we have temperature in degrees Celsius, and these the boundaries that shown in the reds are called phase boundaries, and here on this region you have liquid water, solid ice, and this is vapor region. Okay. So, for one component system the composition is held constant because there is no variation of component, and hence the phase diagram is plotted against pressure versus temperature. And here you can see the triple point O, where all the three phases coexist, and all other boundaries the two phases coexist. For instance, if you take this boundary, this is the boundary between solid phase and liquid phase, and hence on this boundary both solid and liquid coexist, and this is the boundary between solid and vapor, and hence solid and vapor coexist. On this boundary you have liquid and vapor, and hence these two phases coexist on that boundary for various temperatures and pressures. Okay. So, now what is the criterion for finding the number of phases that can coexist within a system at equilibrium? I am sure that all of you are familiar with this Gibbs phase rule, which says that P plus F equal to C plus N, where P represents the number of phases present, F represents the degrees of freedom, C, we will see what do we mean by degree of freedom, C is the number of components comprising the system, N is the number of non-compositional variables. Here non-compositional variables are temperature and pressure. All right. So, the number of components are comprising the system, how many components are there? It is a unary phase diagram, and hence C is equal to 1, right. And now the number of phases present and degree of freedom is something that we will look at, and the number of compositional variables are 2, N equal to 2. Okay. So, now let us look at it. If you are in the liquid phase, how many phases are present? Only one phase, right, it is a liquid phase. So, P equal to 1 and number of components equal to 1, N equal to 2, N is number of non-compositional variables. So, we know that P plus F equal to C plus N, right, that is what we have written. So, using that, F can be written as C plus N equal to 2. So, C plus 2 minus P, that equal to 2, which means we have a degree of freedom to be 2. That means you can actually, from this position, you can move either along the temperature direction or pressure direction independently. You can move in any way. You can move this way, this way, this way, this way, this way, this way, all these are possible. Even if you move, you will still remain in the same state, in the liquid phase only. That is what we mean by degree of freedom. So, F equal to 2 means two external variables, that are pressure and temperatures, can be changed without having to leave the liquid phase region. You will still be in the liquid phase region. All right. Now, you are on the boiling point line, that is liquid vapor interface. So, as we know that this is a two phase, on this line two phases coexist. What are the phases? The liquid phase and vapor phase coexist. So, the number of phases are 2, and C and N will be the same, and as a result your F will become equal to 1. What is the meaning of that? You have only freedom to choose one of the external variables to be chosen. So, this means that either temperature or pressure can be changed while still being on the boiling point line, but the other variable is forced to change too in its own way. That means you can only move this way. So, you can choose what should be my temperature change, and automatically pressure change should be decided by this guy, right, this line. But if you want to move in any other way, then you will be leaving the two phase region, right. So, that is the degree of freedom 1. Now, let us look at the triple point. So, how many phases coexist here? Both solid, liquid and vapor. Sorry, not all three, solid, liquid and vapor. All three phases coexist at the triple point, and hence number of phases present are 3. And then if you calculate F, it is 0. That means you cannot change either pressure or temperature if you want to be in that region, that is a triple point. Here triple point is only a point, right, and hence you do not have any degree of freedom, you cannot move at all. The moment you move, you are going to leave that region and you are going to change, go to another region. So, this means that no variable can be altered to remain at that state. All right. Now, let us look at, we have discussed the solubility limit, and there are certain rules put forth by Hume-Rothery. They are famously known as Hume-Rothery's rules for the formation of solid solutions. First of all, any thermodynamic process that occurs seeks to minimize its free energy, that is important. So, the free energy can be written as delta H minus change in free energy is equal to delta H minus T delta S. So, if in a thermodynamic process, the process should happen in such a way that this delta G is non-negative, sorry, delta G is non-positive, that means it should be negative. Only when delta G is negative, that is when you are continuing to reduce your free energy, as we have discussed here. So, in a solid, atoms of the solute must fit either substitutionally or interstitially, so that the change in free energy is non-positive. This is the requirement. When you are adding a solute atom to solvent atom, and they should fit into the solvent cloud, but effectively resulting in net reduction in the free energy. Only then such a thermodynamic process is feasible. Okay. So, what are the Hume-Rothery's rules? The greater the difference in size between solute and solvent atom, the lower the solubility. That means, if you want to have higher solubility, for instance, if you are talking about binary phase diagrams, if you want to have higher solubility, the size of both the components atoms, the solvent and solute atoms sizes should be almost similar. There should not be huge size difference between them. So, 100% solubility of A in B and B in A is possible if the size difference is less than 8%. And if your size difference between atom A and atom B is greater than 15%, there is almost no solubility. We said 0%, but it is almost no solubility, it will not dissolve in that. Suppose if the difference between A and B is greater than 15%, then the materials do not get dissolved. For them to make a substitutional solid solution, the rules that we are talking about here are true for substitutional solid solutions. The numbers may be very different, little different for interstitial solid solutions. So, but here we are focusing on substitutional solid solutions just to get an idea. And again, the solubility is will diminish if the electronegativity values of these two atoms are very different. So, if you want to enhance the solubility, there should be their electronegativity values also should be very close to each other, and the valence number, the difference in valence number should also be very close. So, should be very less. That means, the valence number of atom A and atom B should be as close as possible in order to have greater solubility. And 100% solubility is possible only if solvent and solute have same equilibrium crystal structure. That is another important thing. If a solvent atom is A is FCC and solute should also be FCC, only then you will have 100% solubility. Otherwise, you will not have 100% solubility. Alright. So, these Hume-Rotheris rules that we have discussed here are primarily suggested based on observations, and these 4 rules that we have written are valid for all the substitutional solid solutions. Alright. So, now let us look at the binary phase diagrams. As we have discussed, when we say binary phase diagrams, you have 2 components A and B, and here as we have discussed that for describing a phase diagram, you will have 3 variables, 3 independent variables. What are they? Pressure, temperature and composition. So, in this course, when we are talking about binary phase diagrams, the 2 independent variables that we are choosing are temperature and composition, and typically that is how it is done for most of the phase diagrams, and pressure is usually held constant at atmospheric pressure. So, most of the phase diagrams that you would see in the literature are drawn with composition versus temperature at 1 atmospheric pressure. And if there is a change in atmospheric pressure, when there is change in pressure other than atmospheric pressure, then the phase diagram will change when you are drawing between temperature and composition. But most of the phase diagrams that we will be discussing, not all the phase diagrams that we will be discussing in this class are done at atmospheric pressure, and that is also true for several phase diagrams that you would come across in the literature. So, the binary phase diagrams represent the relationships between the temperature, composition and quantities of phases at equilibrium. What are the different quantities of, what are the different phases and what are their quantities? This is something that will be clearly described by a binary phase diagram. And note that the microstructure, the underlying microstructure of an alloy is significantly influenced by the above parameters, particularly the composition and the temperature. These 2 guys are going to significantly influence the microstructure. So, the binary phase diagrams help us in predicting phase transformations and the resulting microstructures. How a particular phase transform to another phase and the resulting microstructure from through these phase transformations is something that we will understand through binary phase diagrams. Okay. So, in this module, in this course, we will be discussing different types of binary phase alloys. Okay. So, here we have made a classification. So, let us say you have a alloy A or metal A and metal B. We are only talking about metallic alloys. So, metal A and metal B, and if the first classification is that if metal A and metal B are soluble in liquid state, completely soluble in liquid state, that means there is 100% solubility possible for A in B and B in A, right. When is that possible? When some of the rules that we have discussed before. Okay. So, the primary classification is that we are saying that they are completely soluble in liquid state. So, of the materials that are completely soluble in liquid state, now the first type of alloys that we are going to discuss are called isomorphous alloys, which are also completely soluble in solid state. So, isomorphous system is a system of alloys in which components A and B are completely soluble in liquid state and completely soluble in solid state. That means, A is soluble in B and B is soluble in A completely. And then type 2, in type 2 we will look at a system wherein there is complete solubility in liquid state, but there is no solubility in solid state. There is no solubility in solid state. And when we are discussing this type of a system, we will look at a specific very important reaction called eutectic reaction, or we will also discuss something called this type of alloys are called eutectic alloy system. And now the third one is somewhere in between these two. You have complete solubility in liquid state, you have partial solubility. So, that means it is not complete, partial solubility. That means there is a limit to solubility of A in B and B in A in the solid state, whereas there is no limit to solubility in the liquid state. That is what we call type 3 alloys. And then we will look at a specific, again this is also completely soluble in liquid state, type 4 alloy, but here we will see a special kind of a system called congruent melting intermediate phase, alright. And then we will look at the type 5 alloys, in which we see a special reaction called peritectic reaction, okay. So, all the first type 1 to type 5 alloys are such that they are completely soluble in liquid state, in the solid state their solubilities are changing, right. And then we will look at a type 6 alloy, which is having a partial solubility in liquid state. And then we will look at type 7 alloy, which has complete insolubility in liquid state and solid state, right. And then we will also look at the transformations in solid state. Here all these transformations here are liquid to solid. Here we will see solid to solid state transformations. The 4 important transformations called allotropic transformation, order disorder transformation, the eutectoid reaction and peritectoid reaction, okay. With that I will stop here, and in the next class we will look at the isomorphous alloy systems or type 1 alloys. Thank you.